Hey everyone, welcome to chapter 14, the last chapter in the course. All right, so to start off, fluids, which is what chapter 14 is about, we have to talk about Pascal's principle, right? And that talks about, or that describes how as you move up or down in a continuous fluid, a fluid being a gas or a liquid, as you move up or down, the pressure at that height or depth will change, right? Specifically, the pressure depends on the height, okay? So let's take a look at what I mean. Actually, first, let's write down some assumptions, okay? We are assuming a few things, right? Assuming first that the density is constant. So the density rho, right, and this is Greek letter rho, right, not lowercase p. That's kind of a script p. And that stands for the density, okay? The density rho is constant. That's the first assumption. Secondly, there are no horizontal changes in the force, right? So no horizontal forces. And we'll be talking about just a random volume of fluid, okay? A given volume of fluid. And in that case, there are no horizontal forces. There's only vertical forces, which I'll show you momentarily. The third thing we need to assume is that this is a continuous fluid. Okay? There are no jumps in density. So I think these three assumptions play all off of one another, and they're very related. Okay? So with that being said, let's take a look at some general volume of fluid. I'm going to make it easy on ourselves and draw this as a rectangle. Okay? In this derivation, you could do any volume, right? But I think a rectangle is easiest. We just need a volume with some change in height. So we'll call this at height y1 and this at height, well, y2, which is really y1 plus some delta y, right? Plus some thickness or some h, okay? So assuming this is a continuous medium, right, meaning there are particles of either water or air molecules at every little tiny point in here, right, such that they all exert a pressure on their neighbors. Okay, so as you move through this height, either up or down, that will change the pressure. Okay, evenly, continually, uniformly, okay, or smoothly, if you will. So that means that there's a pressure pushing up on the bottom of this volume of air, okay? Or rather, it's pushing up on the bottom surface of this volume, okay? So let's call that force 1, okay, for right now. There's also a force from the fluid above this volume, right, pushing down. You can think of this force coming from the weight of all of the fluid above. If this is air, it's the weight of all the air above this given height. Okay. Since these are actual air molecules or water molecules or actual particles, right, they have some mass. And so collectively, they have some weight. So this volume of fluid will have some weight. And I just realized I can't draw it from the center of mass. So I'm going to draw it just to the side. So this mass has a weight. I'm going to call it mg, right? That's the collective force of gravity of this system of particles. All right. I should also say that both the top and bottom have some area. We'll call that A, right? So the volume is then area times this delta y. Okay. Let's see. What else do I need? I need to assume that the region of fluid around it is just some standard density rho. okay? And yes, that's the same as in here as well, okay? All right, so now we have all of the forces. There are no horizontal forces, okay? Just vertical forces. And that really comes from the force of gravity on each of the particles in the volume, right? Collectively, they have a weight mg, and on the bottom, it's the pressure per area on the bottom surface that exerts a force upwards. That's due to all of the particles underneath, okay? And conversely for all of those above. So let's write out a second law equation for this free body diagram, if you will, okay? So let's call up as plus y. And so we have F1 minus F2 minus the weight of this volume, okay? And that's all 0. And that's another key, right? I should have put this as a fourth assumption. This packet of fluid, air or water or what have you, is not moving. It's stationary. Pascal's principle governs stationary fluids. Okay? We'll get to moving fluids with Bernoulli's principle towards the end of the chapter. But for right now, this is not accelerating, not moving, so the net force is 0. Okay? Now, we need to rearrange, or rather redefine, what the mass of this volume is, right? How can we put mass in terms of the density? Well, over here, we know that density equals mass per volume. Well, that means mass is then density times volume. And as far as this volume here that I've written, well, that's just simply area times height. So we have rho times A times the height, which was delta y. And I said this is delta to allow us to have any height volume, right? It doesn't have to be a singular height. It can be any height. So you could just as easily put h there too, okay? All right, so this is another way to write the mass of this volume of fluid. I'm going to take that and plug it in to our free body diagram equation. So minus rho A delta y times g equals 0. Okay? Now, I need to write these forces on the underside and top side of this volume. I need to write these in terms of area and basically density and volume as well. Okay? So also remember what pressure is. Pressure being capital P. Pressure is simply force per area. Okay? So rewriting that means I have pressure at height 1 times the area of the bottom surface minus the pressure at height 2, right, the top side, times the area of the top side. Right? Those two areas are the same, right? And that's also the same as the area in the third term here. And I'm actually going to, let's leave that. Whoops. Let's leave it on the left side of the equation for right now. So if I do all this, we can see that the area cancels out, right? And I'm going to take the pressures and put them on the right side of the equation, which will leave us, if we do that, we have P2 is positive minus P1 equals a negative rho delta y times g. Okay, so what I did was just take this term, move it over, and then this term, move it over. They change signs. Okay, and so now what we have is pretty much a change in pressure, right? P2 minus P1, final minus initial, if you will. So I can write that to, yeah, we'll do it like that. So delta P, I'm going to divide the delta y to the left side, and thus we have the following right here. And this is one way to write Pascal's principle. So what this says is that there's a change in pressure for the same change in height, right? Or rather, a change in pressure is directly proportional to a change in height. And that proportionality, right, that amount is a constant. It's a negative, but it's a constant. The density rho was one of my assumptions. The density is constant and the local acceleration due to gravity is constant, right? So this is after chapter 13, right? We're going back to remaining close to the surface of the Earth. So the value for little g stays constant. It doesn't change, okay? So let's write this another way, actually. Let's put this in calculus speak. Well, that means that if you have dP, right, a change in pressure, if you integrate over that change in pressure, you should get a change in height. So rather, let's do P1 to P2, or rather, let's just do from point 1 to point 2. Then you get negative rho g times integral of dy from 1 to 2. This is another way to write Pascal's principle. And so if we evaluate this out, right, we get P2 minus P1, and then negative g, or sorry, rho g times y2 minus y1. And this says that, here, let me write a picture real quick. Picture, where I want my picture. Let's erase all that busy work right there. And now if I have, say, some height, y1, and then another height up here, y2, and if we go up, right, that's the positive direction, what does this equation tell us? Well, y2 minus y1, that should be a positive value, right? The value for y2 is greater than y1. Think of y1 being the ground at height 0, say, okay? So if you go up, y2 will be larger. That means this right side of the equation overall will be negative. And if the right side is equal to the left side, that means the difference in pressure between points 2 and 1 will be a negative. And in fact, that should match your intuition, right? If you go up in the atmosphere, right, say you hike or drive up to the top of a very tall mountain, the pressure up there at P2 is less than the pressure down at sea level or on the valley floor. So P2 minus P1 will also be a negative value. You can also distribute the negative sign. So then you would get rho g times y1 minus y2. And this says the same thing, just in maybe a different way to look at it. Okay? So this is Pascal's principle. As you change height, right, a vertical height, you change pressure, exactly proportional to that change in height. And the same exact analysis works if you go down, right? If you go down, pressure at P1 will be greater than P2. Thus, this will be a negative value, and then this side, did I say that right? Yes. This side, y1 will be less than y2. So this will be positive, and thus will make it negative. Right? This also works for underneath, say, the ocean, right? Underneath water or inside a body of water. The same exact up and down, same exact sign conventions work the same way. Okay? So this is Pascal's principle, two ways to look at it, right? In an algebraic way a little bit, and then with calculus. All right? Thanks for watching.